Give a large language model a small task, like write a story, and it will output familiar words, like once upon a time. It seems almost effortless, but underneath this simple interaction is a large sequence of mathematical operations. In this video, I will show you how LLMs work, how we can make them faster by using pruning, and tell you about our method that we developed, which is called Tanos. It's like you click and half of the parameters are gone. The model first breaks the input into tokens. The tokens are represented by vectors, long list of numbers that encode information the model can process. For us, it's natural to work with words. That's how we used to communicate. But for machines, they prefer to work with numbers, with vectors. They like this kind of high-dimensional representations. And for every word that we know, LLM is trained to encode it into some high-dimensional space. Given those tokens, LLM produces a probability for every possible next token. In our example, once has the highest probability, so it must probably be selected as the next token. Then, the selected token is appended to the input, and the whole process repeats. After once, the distribution now favors upon. Then the model produces another token, and another, generating text one step at a time. So the visible behavior is simple. Input goes in, probabilities comes out, and the difficult part is everything happening inside this box. Inside the language model, the input passes through a sequence of blocks. Every block changes the embedding vector and gives a transformed version to the next block until we process all blocks. Let's consider the very first block. On the input, it has the matrix X with embeddings for words. Remember that X is a two-dimensional matrix where every row represents a token from our text. Now we have two matrices that are used to create queries and keys. For every token, we have a query vector. This vector shows what information the token is trying to find in other tokens. We also have a key vector for every token. The key vector shows how related every token is to our particular query. The dot product between queries and keys shows the correlation between tokens, how important every token is for that particular selected token. Now we compute the value matrix, which is a projection of token embeddings for the purpose of the particular query of the attention head. It selects the most important information that our attention head needs for that query. After that, we mix this information by using QK score we computed previously. We normalize the QK score by using a softmax, so every column of QK matrix sum up to 1. Then we have down and up projections with normalizations to get the final output of the block. The exact architecture designs changes from model to model, but the overall pattern is the same. The important observation for us is that the vast majority of parameters for LLM are stored in linear layer matrices, and the same large weight matrices appears in block after block after block. This is why modern language models require so much memory, and why we should focus on linear layer weights. If some of those weights are redundant, removing them can make the model smaller and can enable faster inference. The challenge is to remove weights without destroying the behavior of the model that made the model useful in the first place. Consider the weight matrix of one linear layer, which we call W. Every dot is one learned parameter. The weights have different values, so the most obvious pruning rule is magnitude pruning. Rank them by absolute value and remove the smallest ones. That rule is cheap, but for large language models it's often too crude. A numerically small weight can still matter if it multiplies an important input activation. Our problem is that we only consider the weight matrix W. But for calibration input X, the output of this linear layer is W times X. After pruning, we have a new matrix W hat. We want the output to remain as close as possible to the original output. So our loss is the squared Fabinius norm of W hat X minus Wx. Fabinius norm is just a sum of all squared entries of the matrix. Equivalently, if delta is the change from W to W hat, the loss is the squared norm of delta times X. We can rewrite the same loss in the row-wise manner. Every element of the sum here is an L2 loss of the corresponding row from the matrix. That means that we can study one row at a time. This makes the problem much simpler, since if we can solve this problem for a single row, then we can solve this for all rows by just applying the same algorithm to every other row. Let's focus on row K And suppose the weight in column Q is one we consider for removal. The vector delta describes how that entire row changes. Our goal is now clear. Choose delta so that delta times x is as small as possible, while forcing the selected weights to become zero. This compact objective is a foundation for many pruning and quantization methods. Let's consider the simplest possible case. We remove one weight and leave every other weight unchanged. Then we multiply this sparse change by x. The change is one row and it's multiplied on every column of x. But we can see one important thing. In the entire row of delta, only one element has non-zero value. So only one element will give non-zero result after the multiplication. That means that we need to take only one row from the matrix X. Finally, we can rewrite the full row of X in a more compact way to make the formula look nicer. The loss after removing a single weight is the squared weight value multiplied by the squared norm of the corresponding input activations. In plain language, a weight is safe to remove when the weight is small, the input feature it acts on is weak, or both. It is an optimal brain damage style formula which was used in the method called Wanda, pruning by weights and activations. We can compute the score for every weight and use it to rank pruning candidates. Then we remove half of the parameters with the smallest Wanda score. This works much better than a simple magnitude pruning, but there is an important limitation. This solution is optimal only if you remove a single weight, but we remove a large portion of parameters. It also assumes the weight we keep are frozen, but why not to slightly adjust them to compensate for a damage we caused by removing red weights? This idea leads to a stronger method. We have exactly the same objective that we want to minimize. For one row of the weight matrix, it's the squared L2 loss. Now consider a more flexible version of the pruning problem. We want to remove one particular weight, WQK, but at the same time, we allow every other weight in the row to change, so that surviving weights can compensate for the damage caused by removing this parameter. We formulate this constraint optimization problem using a Lagrangian. The objective asks for the smallest possible increase in the squared output error, while the constraint forces the chosen parameter to disappear. The matrix H is XX transposed, which is simply the hashing of this squared error objective. It captures both the scale of the input features and correlations between them. Solution for this Lagrangian gives us two important things. The first is the update rule. It tells us how every remaining parameter in a row should change after a selected parameter is removed, so that these parameters compensate for the damage as effectively as possible. The second is the silency score. This metric tells us how much the loss will increase if we remove this particular parameter and then optimally update all other parameters to compensate for it. Therefore, we can compute this score for every weight and identify the least important parameters. This is the central result of optimal brain surgeon, OBS for short. It gives us both a way to rank weights for removal and a way to reconstruct the surviving weights afterwards. Let's look at how we can apply this. We compute the silency score for every weight and select the parameters that should be removed. In the animation, these selected parameters are shown in red, while the green parameters are retained and allowed to change. Because the loss decomposes row by row, we could process every row independently. Let's begin with the first row. Several parameters have been selected for removal. We now move through the row from left to right. First, we encounter the first parameter that needs to be removed. We set it to 0 and apply the update rule so the other parameter in the row slightly moves so they can compensate for the error. Then we continue along the row until we reach the next parameter that also must be removed. And here we encounter a problem. The update rule was derived for removing one parameter under the assumption that every other parameter is free to change. But the first parameter has already been removed. During the next update, we cannot allow it to become non-zero again. This is very similar to the carpet. When you press it down in one place, you create two bumps somewhere else. So you have to press it anywhere else and make sure that this place will not be popping again. So let's try to apply this example with carpet. The weight that was already removed excluded from every later update. Conceptually, we remove the corresponding row and column from the hashing and continue with reduced system. After removing the second parameter, we have two coordinates that must stay fixed at 0. So the active hashing is reduced again. We repeat this procedure until every selected parameter in a row has been removed. After completing the first row, we repeat the same procedure for the second one, then the third, the fourth, and so on through all C rows of the matrix. At the end, all selected parameters have been removed, while the retained parameters have been adjusted to compensate for them. In principle, this works. In practice, it's completely impractical. A naive implementation would need a different sequence of reduced Hessian systems and different reduced inverse for every row and after every removal. You have to apply these update rules for every single row, and as you remove parameters, you have to recompute Hessian again and again. Also note that we didn't use the fact that all rows have the same Hessian. This gives us a hint that we can somehow simplify it and parallelize to make it work for all rows at the same time. This is precisely the difficulty that SparseGPT solves. Instead of completing one row at a time, SparseGPT considers the weight matrix column by column, moving from left to right. We begin with the first column across all rows. At that point, every row uses the same B by B Hessian system. First, consider the parameter in the first row. If this weight is not selected for removal, we keep it and move on. Next, consider the parameter in the second row. This weight is removed. We set it to 0 and use the update rule to parameters in a row. We continue moving downward until the last row. Now, SparseGPT introduces the key simplification. Once the column has been processed, it's excluded from all future updates for every row at the same time. This happens whether a particular weight in the column was removed or preserved. In other words, after finishing the first column, we declare that only parameters to its right might still change. Every value in the completed column is now fixed forever. Because the same column is excluded for all rows, SparseGPT doesn't need a different Hessian for every row. The entire weight matrix can share the same reduced system. SparseGPT now moves to the second column. The first column fades because it can no longer participate in the optimization, and the active Hessian shrinks from B by B to B-1 by B-1. Again, we process the current column from top to bottom. Selected weights are set to 0, preserved weights remained unchanged, and the compensation caused by removal is propagated only to the parameters on the right. When the second column is complete, it's fixed as well, and the active system shrinks one more. The algorithm continues in this way from left to right. At every step, it selects one column, sends the updates only to the unprocessed part of the matrix, and then permanently fixes the current column. This column-wise order is what makes the optimal brain surgeon practical at LLM scale. However, the reconstruction creates another problem. The parameters to the right can change significantly as they compensate for earlier removals. Suppose we computed one pruning mask in the entire matrix at the very beginning. That mask would specify in advance exactly which parameters should eventually be removed. But while SparseGPT moves from left to right, the unprocessed weights are continuously changing. Their silency scores can therefore change as well. So when you use the SparseGPT updates, these columns from the right, they constantly updating, meaning that maybe we should recompute the mask for them, because the ordering of importance might also be changed. For this reason, SparseGPT groups columns into relatively small blocks and constructs the pruning mask locally. For the current block, it computes silency scores using the current, already updated weights, and chooses which parameters to remove only inside that block. It then processes the block column by column. The selected weights are removed and their compensation updates are propagated into parameters located farther to the right. After the block is complete, SparseGPT moves to the next block and computes the silency score there using the newly updated weights. In this way, the mask for every new block reflects all the changes accumulated while pruning the earlier blocks. SparseGPT repeats this procedure until it reaches the end of the matrix. This solves the stale mask problem, but it also reveals two questions that motivate our own research. The first question concerns the update rule inside a block. SparseGPT still processes the selected parameters sequentially, one column after another. The total result is built by accumulating a sequence of single parameter updates. But the joint effect of removing several parameters doesn't in general equals to the simple sum of this effect obtained by removing these parameters independently and sequentially. If several parameters in the same block must disappear, we should consider them together and find the optimal compensation for the entire set. The second question concerns the local pruning mask. Suppose we want 50% sparsity across the entire matrix. SparseGPT removes 50% of the parameters inside every local block. This imposes a stronger condition that we actually need. We require not only 50% sparsity globally, but also exactly 50% sparsity in every individual block. One block might contain many unimportant parameters that can be removed safely, while another might contain much more important parameters. A fixed sparsity target per block still forces us to remove the same fraction from both. At the same time, we cannot simply compute one global mask at the beginning, because the weights and their scores change during pruning. Our method, Tanos, is designed to answer both questions: how to remove several weights jointly and how to use global importance information without freezing the mask in advance. Let's begin with the first question and derive the joint update. Instead of one constraint, we now have S constraints. The weight at position Q1 through Qs must all become 0 together. The crucial point is that their effects are coupled. If two inputs are correlated, the best correction for deleting both weights is not generally the same as applying two independent single weight corrections, one after another. The solution of this constraint problem is a closed-form formula for a joint weight updates. It might look a bit complicated, but what it does in the essence is simple. It shows how all parameters in a row should be changed if you want to remove a selected set of parameters colored in red. It makes the selected set of parameters to be exactly 0 and adjust other parameters to compensate for the error caused by removing parameters. The vector U contains values of weights being removed. R contains the corresponding rows of the inverse Hessian. R hat is the small square submatrix that captures how the coordinates that are selected for removal interact. This joint update requires inverting S by S matrix, which might be expensive, so Tanos applies this solution to manageable column blocks. Within a block, we remove several weights at a time and compute one coupled correction. The same joint procedure is applied row by row. After the current block is finished, the algorithm advances to the next block and repeats until we complete the last block of the matrix. This answers the first question. Instead of approximating a multi-weight removal by a sequence of independent updates, Tanos computes the optimal joint compensation for all selected weights in the current block. Now let's answer the second question. How can we make a mask to be local but doesn't force it to have a fixed sparsity level? Suppose our goal is 50% sparsity. We know the total number of weights that must eventually be removed from the full matrix. At the first step, Tanos computes the Van der score for all parameters. We then identify the global set with the smallest scores, parameters that are currently best candidates for removal. However, we don't remove all of these parameters. We instead, from the full global mask, take only the part that lies inside the current block. The selected weights in this block are removed jointly, and the surviving weights are updated. Then we move to the second block. Part of the total pruning budget has already been used. We know how many weights must be removed in total, and we know exactly how many were removed from earlier blocks. Their difference is the number that still needs to be removed from the remaining part of the matrix. Because the weights have changed, we recompute the Van der score for all parameters in the entire remaining region. We then select exactly the required number of lowest scoring weights to form a new residual mask. Once again, we apply only the portion of that global mask that lies inside the current local block. This process continues until the global pruning budget reaches 0. This result combines two properties that we wanted. First, mask continuously adapts as reconstruction changes the weights and their Van der scores. Second, we don't impose the artificial requirement that every block must have the same sparsity. One block might lose many parameters and another only a few. This table summarizes the trade-off between methods. For clarity, the complexity expresses assume a squared linear layer, and B is the Tanos block size. Changing B changes the balance between the size of each joint system and the number of blocks that must be processed. Magnitude pruning is the cheapest and needs no calibration data, but it neither reconstructs the surviving weights nor models joint block removals. Vanda adds calibration activations, so its mask is data aware, but it still leaves the retained weights unchanged. SparseGPT uses calibration data and update weights, and its updates are organized sequentially. Tanos includes calibration data, weights reconstruction, and the joint block update. As expected, this extra structure brings extra computational cost. So the natural practical question is, how can we implement Tanos so all these joint systems are solved efficiently enough to use them on large models? Unstructured masks create an implementation problem. One row might have only one selected weight in the current block, another might have two, and another might have three. Their linear systems therefore have different shapes, which prevents using a batch solve on the GPU. In the example on screen, the maximum number selected in any row, which we call smax, is 3. We solved it in the following way. Tanos pads every row to the same maximum size. We pad the removed weights vectors with zeros, we pad the corresponding matrix rows with zeros, and in the extra part of the small interaction matrix we insert identity matrix. These dummy entries are neutral, they don't change the real update, but they make every system the same shape. Now, the equations are uniform across rows and can be executed with batch PyTorch operations, instead of slow nested loops. This chart reports pruning time for different model sizes. The horizontal axis is model size, and the vertical axis is pruning time. Of course, Wanda remains the fastest method, because it doesn't reconstruct the retained weights. Between the two reconstruction methods, Tanos is faster on the smaller models. These methods are roughly tied around the 3 billion parameter point. This shows that efficient implementation can make a huge difference, so even more complicated method can work faster. That happens because SparseGPT has to process a matrix column by column, whereas Tanos can process all weights in a block in just one step. Now we need to answer the most important empirical question. After pruning, how good is the model? Let's return to next token prediction. The model assigns a probability to every possible next token, and the real next token has some probability under that distribution. If the correct next token receives high probability, the model is not very surprised. If it has low probability, the surprise is large. Formally, token level surprise is minus the logarithm of the probability assigned to the correct next token. We average the token log level probability over a text corpus and then exponentiate the result to obtain perplexity, the standard language modeling metric. Lower perplexity is better. We begin with unstructured pruning on smaller models. After naive magnitude pruning, perplexity rises dramatically. SparseGPT is significantly better, and it's better than Wanda. Tanos produced the lowest perplexity. On larger llama models, the result is more mixed. Tanos is best on 1 billion parameter model. On larger models, Wanda is slightly better, which is kind of surprising. A more cheap and more inexact method can give you a better result sometimes. In unstructured pruning, Tanos is competitive, but it doesn't win every model. For Llama 3, SparseGPT is best at 1 billion, while Tanos is best for larger models. This is the honest unstructured results. Several wins, strong overall performance, and small margins across the best data-aware methods. Tanos also supports a structured pruning. Such structures might be more hardware-friendly than arbitrarily unstructured sparsity. In 4-to-8 structured format, Tanos obtains the best perplexity in 6 of 8 models. This supports our central motivation. When several weights must disappear together, modeling their joint effect becomes especially valuable. The 2-to-4 pattern is even more important in practice. NVIDIA Ampere's GPU provide optimized core support for this specific format. Here, Tanos achieved the best perplexity in 7 of the 8 configurations. The overall picture is therefore nuanced but consistent. For unstructured sparsity, our method is competitive and produces the best result in several models. For the regular structured patterns, Tanos wins most of the configurations. We can see that pruning is not only a decision about which weights to delete, it's also a reconstruction problem. Once several weights disappear, how should all the surviving weights move together so the model behaves as if as little as possible had changed? This is the problem Tanos is designed to solve. Thank you for watching this video. This is the first video on my YouTube channel. I hope you enjoyed it. If yes, please give me the like and write some comment. If you want to play with the repository or see the paper that we wrote, all links will be in the description down below. And yeah, I hope you will have a nice day.